Hi guys, today we are going to study the problem of degree of freedom of a couple oscillators. The system consists of two pendulums connected by a spring constant K. Let us see the figure. I did a little figure here by hand. We got pendulum 1 with mass M1, length L1, and the vertical displacement is theta 1. The pendulum 2 has a length L2, mass M2, and the vertical displacement is theta 2. And their pendulums, the masses, are connected by this spring. Indeed, we are going to study today the problem in which both lengths are equal, L1 equal L2, and also the mass will be equal later on after video will, but for now let's say N1 and N2. The the perturbation or the deformation of the spring is given by this by x1, which is L1 times sine of theta 1, and this Lx2 will be L2 times sine of theta 2. So the formation of the spring will be x1 minus x2. But let us see what I'm going to do today. First, I'm going to derive a Lagrangian of this system using the angles theta 1 and theta 2 as generalized coordinates. Then, we are going to write down the Lagrangian equation of motion. Because this is a system of two degrees of freedom, we have equation of motion for theta 1 and equation of motion for theta 2 for the pendulums. After that, we are going to consider the case in which the oscillations of the pendulums are much smaller than 1. And although later we are going to solve the equation of motion assuming that the initial conditions are theta 1 equal theta 0 at time equals 0, and at time equals 0 the initial condition for theta 2 and the velocity theta 1 dot and theta 2 dot will be 0. Let us start then. Here I did just to show you that if we depart the pendulum, a pendulum from the equilibrium position, which is the lower point, we will get an height equal to L, which is all this, minus L cosine theta. This is a height H. L times 1 minus cosine theta. This is very important for today. The Lagrangian is defined as this. The total energy, kinetic energy of the system minus the total potential energy of the system. The total kinetic energy of the system will be the kinetic energy of the mass 1 plus the kinetic energy of mass 2. The total potential energy of the system will be the addition of the potential energy of the first mass plus the potential energy of the second mass plus the potential energy stored at the spring. This is here. This is the kinetic energy of the first mass. It will be one and a half times n1 times L squared times the derivative of theta 1 with respect to time squared. The same way, the kinetic energy of the second mass will be 1.5 times n2 times L squared times the derivative of theta 2 with respect to time squared. The potential energy of the first mass will be n1 times g, which is the acceleration of gravity, times h1. So using this expression here, as I told you before, we will get that v1 will be n1 times acceleration gravity times L times 1 minus cosine of theta 1. Doing similar approach of the calculation, we get that the potential energy of the second pendulum will be m2 times acceleration gravity times L times 1 minus cosine of theta 2. The potential energy stored of the spring will be 1.5 times k times x1 minus x2 squared. In this case, we are going to assuming that the formation of the spring comply with the Hooke's law of force. So the force that the spring is applying, reversing, acting upon the each mass is linear. This is an approximation linear, so there is linear and non-linear approximation here. So if we take equations, operation 2, 3, 4, 5, and 6, and substitute all of these into equation 1, we get the Lagrangian of the system. The Lagrangian of the system will be this beautiful expression here. A bit long, but it's pretty straightforward, yeah? Now, we are going to determine the equation of motion for each mass. The equation of motion is applying the Euler-Lagrange equation will be the derivative first, using the first generalized coordinate theta 1 will be the derivative with respect to time of the partial derivative, the Lagrangian, with respect to theta 1 dot minus the partial derivative of the Lagrangian with respect to theta 1 equals 0. And the second equation of motion will be the similar, but with theta 2. Using the Lagrangian we have here, we just found, we calculate the partial derivative of L with respect to theta 1 dot, we get this, and the derivative of with respect to tan of expression 10 will be n1 L squared, the second derivative of theta 1 with respect to time, twice, squared, twice. And the partial derivative of the Lagrangian with respect to theta 1 will be, using this, remember, the first and the second term the derivative with respect to not a 0, this is 0, this is 0, but there is a contribution and there is another contribution here because depends on theta 1, and we get this. And now substituting 11, the results 11 and 12 into 8, we get the first equation of motion, this one. Now, in order we can divide it, all these equations by n1 times L squared, and we get this beautiful equation. This is the governing equation for the first pendulum. Look, the second derivative of theta 1 with respect to time squared depends on the angle theta of the second pendulum. Using the same calculations, here I show you, here are all the calculations, we get the equation of motion for the second pendulum, the governing equation for the second pendulum. Look, it's very similar to equation 14 for the first pendulum. The difference are first that instead of theta 1 is theta 2, and the second term on the right hand side, instead of being minus k divided by n1, is plus k divided by n2. This is very important. This is very important for this case, for this problem. For the we will show you next. And now that we know the governing equations for the pendulum, let us study the case in which the oscillations are very small. The angle theta 1 and theta 2 are much smaller than 1. In this case, sine of theta 1 is approximately theta 1 and sine of theta 2 is approximately theta 2. We know that cosine of theta 1 when theta 1 is very small is it can be considered equal 1 and cosine of theta 2 will be equal 1. So using this approximation in this equation 19 and equation 14, we get this equation 20, equation 21. And also, look, I assume that the masses in this case from now is m1 equal m2 equal m. Not only the length of the pendulum are equal, but also the masses of the pendulum are equal. So we have this beautiful both equation, linear differential, second order differential equation, but in this case this is minus and this is plus. This is very important from now on. We can say if you take the addition, we addition these two equations, this second term on the right hand side will cancel each other, and we get the next part the solution of the equation of motion. This is the first part. If as I told you just right now a moment ago, we take the addition. The little trick is we add equation 20 and 21. Yeah, we get this beautiful equation. We know the solution. The second derivative of the addition of the angles will be minus omega 1 squared, the addition times the addition of the angles, where omega 1 is omega 1 squared is acceleration of gravity divided by L. If, on the other hand, if we subtract equation 20 and 21, subtract 20 minus 21, we get the second derivative of the subtraction theta 1 minus theta 2 will be minus omega 2 squared times theta 1 minus theta 2, where omega 2 is square root of Gn divided by L plus 2 times K divided by N. The solutions of equation 22 and 23 are straightforward. Functions cosine. Yep. And the solution of 22 will be amplitude A times cosine of omega 1 times t plus an angle phi 1. And the solution of 23 will be an amplitude B times cosine of omega 2 times t plus an angle phi 2, where A, B, phi 1, and phi 2 are constant, which can be determined using the initial condition. Now, we are going to need to go back and let us say them, because if you take the addition now 24 and 25, we get theta 1. Theta 1, the function of t will be A divided by 2 times cosine omega 1 times t plus phi 1 plus B divided by 2 times cosine of omega 2 times t plus phi 2. And if you take this to subtract 24 from 25, we get this result. Now, using the initial conditions, look at time t equals 0. The initial condition will be theta 1 equal theta 0, theta 2 equals 0, and theta 1 dot and theta 2 dot at t equals 0 we get these four equations, 28, 29, 30, and 31. If we solving this system of equations, we get the solution for this problem. This is the solution in this case. This is a system of which satisfies conservation of energy, because there is no dissipation here. So this is our solution for today, and I hope it will help you Thank you very much for your attention.